Okay, today we will discuss the remaining part of crystal defects. In the last video, we have seen the fungal defect and Short-tree defect, which are stoichiometric defects. Today we will take up non-stoichiometric defects. Non-stoichiometric defects. Now, non-stoichiometric defects means there is the stoichiometry of the crystal will not be maintained. That is, if some of the ions will be lost permanently, or some of the ions may be added into the crystal. Okay, so that original stoichiometry is not, expected stoichiometry is not maintained. So that means you are adding excess anions or excess cations or anions. Okay, and therefore the excess anion or cation is added. Present is present. Let me put the word added. I put present. This is that. It may be already there, or you may be adding it purposefully. So that is a better word. So what happens is anion to cation ratio. Anion to cation ratio changes. So this is the characteristic of this non-stoichiometric defects. Changes. Now there are three types of non-stoichiometric defects. So you have three types. One, metal excess defect. Metal excess defect. So as the name itself indicates, you have excess metal ion. Okay. So this can be due to the presence of more excess number of the metal ions, or due to non-metals, non-metal anion is lacking. Okay, deficiency of non-metal anions, that is also possible. So the ratio, there will be more number of cations, more number of cations, metal ions, than anions. That is the meaning, than anions. Now this can be due to, as I told you, it can be due to extra cation or deficiency of anion due to the vacancy created by their absence. Okay. Now the extra cation can be trapped to the interstitial sites also. Okay. So sometimes the extra cation can be trapped into interstitial. You can do it by external work, interstitial space. Okay, artificially you can do it. Okay, so now the electrical neutrality. The electrical neutrality is maintained in the crystal. Electrical neutrality. Remember, electrical neutrality means not conducting power. Talking about the total plus and total minus. Now that is generally maintained in all the crystals. Okay. By sufficient number of electrons, electrical neutrality is maintained by sufficient number of electrons. Number of electrons from the from other interstitial sites. In other interstitial sites. Electrons are moving. You have free electrons will be there in other sites, which will be maintaining the neutrality. Okay. Now, let us take an example for this. That is zinc oxide. Zinc oxide is a very good example. If you take zinc oxide and heat it to a high temperature, what happens is a few molecules of zinc oxide will get decomposed, okay, and will form Zn2 plus ions plus half O2. See, now it is very clear how it is happening. What you have to do is you just take zinc oxide. It's I think it's white in color. It's quite white in color. Now, so when you heat it, the zinc oxide Zn2 plus will be separated, and 1/2 a mole of oxygen is leaving. And when the oxygen is leaving, it leaves the 2 electrons back in the crystal. So you have the Zn2 plus in the crystal in some motive site, and 2 electrons occupying some other site or interstitial space. Okay, so this is what is don't think that it's completely getting converted. Just a small portion will get converted. Okay, now the molecule, the crystal will have a new formula, Zn 1 plus alpha. Alpha is a number of the fraction. Alpha is a fraction which is converted into Zn2 plus O. That means the ratio of the metal has increased. See that. Zn0 is actually, so it is changed from Zn1 O1 to Zn1 plus alpha. See, it has increased by a small fraction, and O1. Okay, but alpha is far less than 1. Very small number, very small fraction. You can just think 1 or 2 molecules of Zn0 converted into Zn2 plus, and corresponding amount of oxygen is getting left. Okay, so what is the general picture of this crystal? Let's have a look at that. As we used to draw the picture, we have the crystal structure here. Okay, then we have again this is the overall picture. All the motifs are arranged in a regular fashion in the usual crystal form, which we have been discussing last quite a few days. So And you have each zinc will be separated by zinc 2 plus. So I'll put the zinc, it is plus. Remember that here is oxygen, here is zinc, here is oxygen, zinc, okay, oxygen, zinc, oxygen, zinc, oxygen, zinc, okay. And this is the usual structure. Now during the heating process, so this is the overall crystal structure. You can connect them. Of course, without connection, you cannot have the crystal structure. Let us complete the figure. When you write the exam, please make that it is properly done. Don't simply try this and time to do it. So here is the overall crystal that is. We are talking about one plane. Okay. Now, now during the heating process, a couple of Zn ions will get separated and they will go into the interstitial space. So one Zn2 plus has come here into the center. Okay, here. So one of them has moved, and 2 electrons will occupy some other place. 2 electrons will occupy at some other place. So this is the overall Zno picture. Okay. Now, so this is a vacancy created by zinc getting converted. Now let's look at an anion vacancy created in the case of sodium. Anion vacancy by heating sodium, sodium chloride, anion vacancy by heating sodium chloride. What you have to do is, you take sodium chloride crystal powder form, sodium chloride crystal, and heat it under, of course, inert atmosphere in sodium vapor. How do you do it? Okay, probably you keep this in an inert tube, maybe purged with nitrogen or something. Okay, or whatever it is. And you keep your sodium chloride and sodium metal here and heat it. Or you can keep them separate. Remember, sodium metal is having a low melting and boiling point related to other metals. So here the sodium will boil. Actually, it melts at 93 degrees Celsius. I don't know the boiling point. So after this, maybe some 300 or 400 degree, it will get vaporized, and that will be, this whole area will be filled with sodium vapor. And sodium chloride is having a very high melting point, somewhere of the order of 700 or 800 degrees Celsius. So this will be in contact with this crystal, and what happens is this will be converted into some of the sodium metal will go into the crystals of this sodium chloride and will form Na1 plus B Cl minus. Na1 plus B Cl minus. Okay. So what has actually happened is sodium metal has gone into the lattice. Sodium is getting Na plus is incorporated into NaCl crystal, lattice site, into the NaCl lattice. Okay. Now this is done by, how does this happen? Uh, so this must be happening due to, yeah, sodium will get incorporated into this, and probably a couple of molecules of Cl minus, a couple of Cl minus will leave as Cl2 gas. Okay, a couple of molecules will go out as Cl2 gas, leaving behind an electron, right? So there will be vacancy created by this. So leaving of the Cl minus creates a vacancy. Which will be occupied by the sodium plus. Vacancy occupied by Na plus. Okay. And the free electron will absorb light. And turns yellow in color. So when you do this, the colorless sodium chloride crystal will be converted into yellow color. So that is a physical observation you can see when you do this experiment. Okay. Now, the site of this electron. Now, if you look at the picture, it will look like this. You have sodium chloride crystal as we draw usually. We have the sodium chloride. I think it's always better to draw this each and every time so that you get really familiar. The plus sign indicates the sodium metal, sodium plus minus, plus minus, plus. Then we have minus here, plus, and here it occupies an electron. Remember, this is the place from where the Cl has gone. Okay, this is supposed to be minus, and that is now the Cl is left as Cl2, and the electron remains here. That's what you have to remember. Then you have the plus, you have the minus, plus minus, plus minus, plus, and again minus, plus, minus, plus, minus. Okay, so here is electron. Electron occupying the place of chloride. Oh, sorry, what did I draw? So the electron is occupied in this space. So this is, and this center is called F center. The center where the electron is occupying after removal of the chloride ion is called the F center. And remember this, the color produced by each crystal, the color produced or given out by each crystal vary is characteristic. Is characteristic. So for example, sodium chloride is yellow in color. Sodium chloride is yellow. If you take potassium chloride and do the same experiment with the potassium, you will get a violet color. And potassium bromide, see what beautiful observations people have made. The violet, this is potassium bromide, it is blue-green. For all these observations, they must have used some or the other for some purpose. All these observations must be utilized in devising certain techniques for identifying certain substances in all. Okay, or even medicines in investigation of diseases, they must have used it. Characterization of different compounds. For many purposes, these observations are utilized. Okay, so that is what you have to appreciate. All these are practically the practical use of this is must have already been implemented. Okay, you must be knowing sensors and all this stuff. We are very familiar with sensors. So these may be the type of observations which has led to the development of sensors and all. Okay, so now let us look at metal deficiency defects. Metal deficiencies. So far we were discussing metal excess defect. Let's look at metal deficiency defects. Metal deficiency defect. What is that? Now this is generally observed in ionic compounds, observed in ionic compounds with metals containing metals, compounds of metals of variable oxidation state. Variable valency or oxidation state. Now see here, this is the moment you think about that, you will always, the first element which will come to your mind will be iron. Okay. So iron oxide crystals, which is known as woostite. Woostite. This is iron oxide crystals, FeO. Okay. Now, some of the Fe2 plus will be lost. So in FeO crystal, some Fe2 plus is lost. And for each missing Fe2 plus, two Fe2 plus are converted into Fe3 plus, 3 plus for electrical neutrality. Electrical neutrality. Okay. So the crystal will be having the formula Fe 1 minus alpha O. So this is 1 minus alpha FeO. It's a new formula of the compound. So what happens? We can picturize this Fe2 plus 2 minus 2 plus 2 minus 2 plus. Now you have again 2 minus. Now here something is missing. One Fe2 plus is missing. So here is a vacancy. Then you have minus plus. Now here it is 3 plus. So the Fe2 plus from here has converted into Fe3 plus. And here is minus. Here is, you have 2 plus, 2 minus, 2 plus. And here you have a 2 minus. And here again Fe plus. So for each Fe2 plus, 2 Fe2 plus has converted into Fe3 plus. Minus 2 plus. Okay, so 2 atoms are converted into right. So this is what has happened. Now when you convert Fe2 plus into Fe3 plus, 2 electrons will be Fe2 plus. Now see here, you are losing one Fe2 plus. Fe2 plus is lost from this side. When Fe2 plus is lost, that means 2 positive charge is reduced. 2 positive reduced in the crystal. Now you have to compensate this. So you have to increase the positive charge. What do? 2 other Fe2 plus. 2 other Fe2 plus. Converted into 2 Fe3 plus plus 2 electrons. Okay. So you have increased the positive charge. See here, 2 positive charge is decreased. Here 2 positive charge is increased. Okay. And the electron will be there, in the interstitial spaces or somewhere in the proper places. Okay. So this is what is happening. In the case of Fe, for a sulfate also the same thing happens. That's another example for a similar type of defect, metal deficiency defect. Okay. So what is actually happens? What happens is this existence of different oxidation state. Here, what is actually happening is existence of different oxidation state. Results in free electron transfer. Oh, okay. Or electron exchange. Or electron exchange. So this conversion has created electrons and they will get transported from one side to the other. And hence it will increase electrical conductivity. So electrical conductivity is increased. Okay. So how is this happening is, see this positive, these positive holes will get migrated. These are the Fe2 plus generated here, and the electron is moving to this side. When the electron is moving to this side, this side will now from here, see, there is a hole here. So into this hole, this will move, and you create a new hole here, and the next some ion will move from here to here. So there is a positive hole created every time. Okay, from one side to the other. So each of these migration will lead to a creation of a new hole, and this type of positive ion movement is what is the basis of creation of p-type semiconductors. P-type semiconductors. Okay, and also this particular phenomenon, creation of new charge and loss of electrons, migration of electrons, that will lead to some metallic luster to this compound. So electrical conductivity is increased, you can note down. And due to positive hole migration, here as I shown you here, the 3 plus will jump here like this. So here a new vacancy will be created, and this will positive hole migration, and this lead to creation of p-type semiconductors. I think we have to study semiconductors. P-type semiconductors. And also it generates a metallic luster to this compound. So for FeS, it attains, this particular phenomenon attains a golden yellow color. Imparts a golden yellow color. Okay, and it shines in fact. And it shines. So it is termed as fool's gold. Mistaken. Okay. Now, two more examples for such crystals is CuS. Remember, this is also variable valency. You have 2 plus, Cu2 plus, and Cu plus, and nickel oxide. Nickel oxide also are examples for this type of crystal, showing crystal defects. Okay. So there's a second type, deficiency, metal deficiency defect. Let's look at the third one, impurity defects. See, impurity defects. Okay, here the presence of foreign positive ions. Presence of positive ions. Other positive ions. Will presence of other positive ions for the missing ones. In the place of the missing ones. In the place of missing ones. So that means it is a substitution type of metal defect, a crystal defect. Okay. Example. Silver chloride crystals or silver bromide crystal. Okay. When 2Ag plus is missing, and what happens is this is replaced by a metal ion which is having the same CD2 plus. This is replaced by CD2 plus. Remember, it's having the same size, almost having the same size, having the same size. Same size. So now what happens is CD is 2 plus, and silver is this is plus only, silver is Ag plus. That you have to remember. So one of the place will be occupied by the CD. Okay, one vacancy occupied, and the other is left vacant. Other is vacant. See, the characteristic have changed. Overall neutrality remains the same. 2 plus is gone, 2 plus is come, but number of atoms is reduced. Okay, and this vacant position will lead to electrical conductivity, semiconductive properties, and this will lead to semiconducting property. Semiconducting property. And also it leads to a color change in color. It's a very important color, I think. So this is an impurity, introduction of the impurity. Okay. So this you can call as an extinct defect. What is the meaning of extinct defect? Extinct, extinct, extrinsic defect. Meaning intrinsic and extrinsic. That is, metal is coming from outside. Okay, a new metal is getting introduced, and a new substance is getting introduced because foreign substance is introduced. Foreign substance is introduced. Okay. Another example, a very beautiful example is uh, carbon atoms. Carbon atoms occupied by or occupied vacancies created by iron. Vacancy of iron, and this is what is called steel. Okay, so incorporation of carbon, small amount of carbon to the point of 0.1 or 1% or even less, far less than that into the iron is what is, see how the application goes. Okay, so carbon is occupying the interstitial spaces or vacancies created by the iron in iron crystal or iron rods or whatever you do. Similarly, four atoms, hydrogen atom is introduced into palladium atom. Okay, palladium atom in palladium crystal. And you know, palladium is a very important catalyst. And now you know how it is acting. Palladium is used in hydrogenation. Palladium is used in hydrogenation. So you introduce the hydrogen atom into the palladium. It occupies a place of some of the palladium atoms. And that hydrogen will get a high energy state, and that will lead to the hydrogenation process. And this is probably, this should be the mechanism by which palladium is acting as a catalyst. And another example is, you know, the diamond. Diamond is actually the impurity of some transition metals. The colored diamond, not the usual diamond, is the impurity of transition metal in the carbon chain. Okay. So this is briefly about the crystal defect. Okay. Thank you.